Hello, my name is Leland, and this is my lab report for lab number 2, motion of a falling object. So as an introduction, the purpose of this lab was to observe the motion of an object falling from a height, then compare the motion to a computational model both with and without drag. An overview, drag played a large role in this observed motion, and the computational model without drag is vastly different as time increases. Our system was the paper ball, and the surroundings were gravity, drag, and air resistance. Some of the fundamental principles included Newton's second law, or the momentum principle, which relates the net interaction between the system and surroundings to the observed position of the system. Our equation here is force is equal to mass times acceleration. Two other useful equations are the velocity update formula, where the final velocity is equal to the initial velocity plus the net force divided by mass times the change in time. And the position update formula, which is the final position is equal to the initial position plus average velocity times change in time. Gravity also played a role in this experiment, and that is the force pulling the ball towards the ground. Here, the gravitational force is equal to negative mg in the y direction, which is negative 9.8 meters per second squared times the mass. And then drag is the force against the ball, and our equation here is negative b times the magnitude of velocity squared times the unit vector of velocity. The procedure for this lab was to record a video of a paper ball falling from 1 meter height, then import the video into Tracker and analyze the change in position for each frame. From there, create a computational model in GlowScript without drag based on the initial position, create another computational model in GlowScript including drag, and then use a spreadsheet to compile the position data for the three models and graphically and visually compare the results. Here is the video from Tracker. As you can see, the ball falls downward. So the calculations for GlowScript. The negative slope indicates a negative velocity, which means the ball is actually falling downwards, which is what we observed. The velocity is not constant, and our initial position is at 1 meter. In GlowScript, we set the mass of the ball equal to 4 grams. We set the initial velocity vector to 0, because there's no initial velocity, and we set the initial position to plus 1 meters high. The delta t was set to 0.033 for 30 frames per second, and because we are not calculating drag, our proportionality constant was 0. The net force is equal to the gravitational force plus the drag force, and then we use the velocity update formula and position update formula to generate our graphs. And here is the position versus time graph for no drag. For the model with drag, the conditions are the same, and then we set the proportionality constant to 0.006. This accounts for drag and was found through trial and error. And here's the position versus time graph for drag. When compiled, we can see the three different models observed, no drag and with drag. And the model without drag is similar at first, but then starts to differ largely. And the model with drag is very close to the observed position versus time. Some sources for error in this lab, there are a few, are rounding, inaccurately tracking the motion in Tracker, and outside forces. And these sources of errors could lead to both minor and major differences. Additional questions. Examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict a terminal velocity? So the model that accounts for drag predicts a terminal velocity, and the velocity becomes constant as the net force approaches 0, meaning no acceleration. But we can also see in the graph that without drag is just a linear graph, and then with drag starts to approach negative 2.5. Additionally, imagine the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? So to calculate this, I set the initial velocity to negative 1 meters per second in the y direction, and it showed that the terminal velocity is achieved, and it's the exact same, except it just happens faster. It achieves this terminal velocity faster. In conclusion, we utilized Newton's second law, the momentum principle, gravitational force, and drag force to model the motion of an object that is falling. We observed and analyzed the position versus time and velocity versus time of a falling paper ball, and then we compared computer models with real-world data. We noticed that the drag is present in real world, and the computational models are not always 100% consistent with observed data. Thank you very much, and I hope this was helpful.